So as we enter in typecheck the body of let type, we need to record the name of the defined type, which I'm going to abbreviate with a capital D, its variants, and the types of the fields that go with each variant. So we'll have a new kind of extension to the type environment that records that D can be x1 or x2, and that x1's field type is tau1 and x2 field's type is tau2. That's how we'll write it in our mathish notation. As we implement it, it means that we have a new kind of type binding. We still have tbind, like we did before, that binds a variable name to a type, but in addition we have a different kind of binding, which is a type definition, which binds a type name to information that says it can either be tag 1 or tag 2 with field types for each of those tags. Another consideration is when we write a type in an expression, like fruit, then it's okay as long as we've defined that type. So when we do let type fruit, then I can use fruit as a type name. If my whole program is just lambda x of type fruit, this doesn't make any sense because the type fruit is not defined. It's a free variable at the type level, and our type checker needs to rule that out in the same way that it rules out free variables at the expression level. So we have a new part of our checker, this single turnstile without a colon after it. So it's just the traditional name in math notation for this function. We'll call it tvarcheck when we implement this function. But this function takes a type such as bool or num and an environment, a type environment, and says whether that type is okay. And it's always okay to write number in Boolean, and it's okay to write down an arrow type as long as the result type is okay to write down. Result type is over here, and the argument type is okay to write down. But you can only write down a type variable, such as fruit, if the current environment has a definition of fruit in it. So we'll need to call tvarcheck in various places. In particular, we have to adjust our rule for functions to do most of the usual thing, right? In the body E, then the identifier, that is the argument to the function, will have type tau1, as long as tau1 is an okay thing to write. So the new part of this rule is right here that says make sure that tau1 is an okay thing to write. If we wrote fruit, is it okay to write fruit? And so on. And when we implement type check, then this adjustment is reflected by changing lambc to do everything it used to do. That's the arrow type here. But before that, just call tvarcheck to make sure that this type we wrote down, possibly fruit, is okay in the current type environment. This is the mathish notation for type checking a let type form, and it shows the various things we need to do. The first thing you see at the top is we take the current environment, type environment, and extend the type environment to get gamma prime here by adding in the information that D has variance x1 and x2 with field types tau1 and tau2. In addition, in this expression, you might use x1, and you use it the same way as a function. So we bind in the type environment the information that x1 itself has type tau1 arrow D. That is, you can use it like a function, give it a tau1, the type of the field, and what you get back is a value of type D. There's a little bit of redundancy here in that the same information is implicit over there, but it's just easiest to repeat it in the type environment. Same for x2, it takes a tau2 and gives you back a D. So with those extensions to the type environment, we also need to make sure that the tau1 and tau2 that we wrote down are valid types, that we don't name a type that isn't allowed. And notice we do this checking after we've extended gamma prime. The checking of tau1 after we've already used tau1 is very similar to letrec, right? This is recursion at the type level, right? And then after we've checked that tau1 and tau2 are actually reasonable things to write down in the first place, now we can go type check the expression E in that extended environment, and we get back a type tau0. On the type case side, then we have this type D that we're dispatching on. So we need to make sure that our current environment gamma includes a definition of D. And it has to define D for x1 and x2. Those have to match up with the x1 and x2 that were written down in the type case expression. x1's field type is tau1, so that means x3 here is going to have tau1 in E1. And that's what we wrote right here. Take the environment, extend it with x3 has type tau1, then type check E1 to get some tau0. x2, x4, and E2 are same. Type check E2 in environment where x4 has type tau2, And we also, in this case, have to get tal 0. That is, both cases of the dispatch have to return the same result, just like both branches of a conditional have to return the same result type, and then that is the overall type for type case. I'll warn you just a little bit, this rule is not quite right. There's one more check we need, but it's kind of subtle, so I'm going to delay that for a minute, and we'll fix it up later. Changing those mathy rules to PLAI typed code, when we have let type form here, then this is where we create a type definition to add into the type environment. Right? That type definition records the type name, variant names, and the field names for each variant. After we created this extended environment, which I called gamma prime before, we make sure that the types that you wrote down for the variants are actually sensible. Those are the two calls to tvarcheck. And finally, type check the body. In an extended environment that starts with the one that has the types, but also adds in that tag 1, the variant name, acts like a function that takes a field value and returns a value of type name, right, which we wrap in a defined t to make it a type. When we type check type case, then we have a lot more work to do. So in type case, we have a type name, and the first thing we do is look in the type environment for that type name, hopefully getting a tdef back. And if we don't get a tdef back, there will be a no type exception raised, because that means the type name wasn't defined. So that's the type name, and then test here is the expression whose value we're dispatching on. So since it's an expression, we want to type check it. We type check it in the current environment, and we expect to get the type of that thing has to match up with the name that we're dispatching on. So when we type check, we hope to get a defined t back with that name, and we need to make sure that those two names are equal, right? The actual type and the type that we mean to dispatch on. And then we also have to type check both of the variant cases, right? The right-hand side for each of those cases. And as we're type checking each of those, we have the argument that is bound in that case to the type for that type for that variance field. Okay. So these are the essential pieces here when we put it all together with extra checking and making sure that the type tags match the defined definitions, tags, and raising suitable errors and so on. That's what it all looks like. Finally, tvarcheck just walks over types to make sure they're okay. So a number and a Boolean type, they're always okay, so we don't complain. In the case of an arrow type, we recur on the argument and result types. In the case of a defined type, we just make sure it's actually defined by looking it up. So if the name turns out not to be defined, we'll raise an exception. Otherwise, the name was defined, and so we succeed.